Hey everybody, and welcome to the first of a couple of videos exploring the interconnections between the three kinds of probability that we introduced last week. Probability as rational degree of belief, probability as relative frequency, and probability as objective chance. Now, in the last video, we looked at the connection between probability as rational belief and probability as chance, and we saw that they were connected by the principal, which essentially said that your rational degrees of belief should defer to known chances, right? So your probability in a proposition x, given that the chance of x is some number, should just be that number, right? In this video, I'd like to look at some connections between relative frequency and chance. So this is what we're going to look at in this video. In doing so, it'll be helpful to consider some concrete examples. So we're going to work with a setup that we've become fairly familiar with at this point, and that is the setup of flipping coins. So let's suppose we're flipping a coin. There's two sides to it, heads and tails. And we can think of ourselves as working in a space where maybe we're going to flip the coin 3 times. So we could have x1 representing the first toss of the coin, x2 representing the second toss of the coin, and x3 representing the third toss of the coin. And then these 3 tosses together could make up our domain or our reference class. These 3 tosses. And let's say that, right, h sub I, right, is just the property that the proposition, excuse me, that the ith toss lands heads, right? So, for example, right, h1 would mean that toss x1 is heads, h2 would mean that toss x2 is heads, and so on. Now, let's suppose that we know the chance of a particular toss. Let's say the chances of the tosses are all the same, right? So, right, that's to say, right, the chance of any proposition hi is equal to the chance of any other proposition hj for all I and j between 1, 2, and 3. So this just means, right, every toss has the same chance of landing heads. And let's suppose for simplicity, right, that this chance is equal to 1/2. And since the chance of each of these tosses is the same of landing heads, I'll denote it with the letter R, and I'll say R equals 1/2. This means that the chance of any particular coin landing heads is 1/2. Now we can think not just about the chance of simple propositions like, is this toss going to land heads? But we can think of the chance of complex propositions, like, for example, h1 and h2 and h3, right? This is the proposition that the coin is going to land heads the first time and the second time and the third time, right? Since chances are probabilities, right, we can compute the chance of this proposition by recognizing that really, right, it's a conjunction between the first proposition that the first toss is going to land heads and the second proposition that the second and third tosses will land heads. So breaking this down step by step, we have that this is equal to the chance of the first toss landing heads times the chance of the second and third one landing heads given that the first one landed heads. Right? This is just an application of the general conjunction rule, right? Now we can do another application of the general conjunction rule, and we'll get that we have the chance of h1 times the chance of h2 given h1 times the chance of h3 given h2 and h1. Right. Now, this is then a general instance of the rule of the probability calculus that's known as the chain rule. It's basically just repeated applications of the general conjunction rule, right? Now, let's suppose that we can make an independence assumption here, right? That the chance of a particular toss landing heads is unaffected by how the other tosses go of the coin, right? So in that case, right, chance of h1 is just chance of h1, and chance of h2 given h1 is just the prior chance of h2, right? Since if the first coin lands heads, it doesn't affect the chance that the second coin will land heads. And similarly, right, the chance of h3 given h2 and h1 would just be the chance of h3, right? So this line here, we're making an independence assumption. Independence of chances, right? So then we have, that the chance of this conjunction, h1 and h2 and h3, is just equal to the product of its individual conjuncts, right? Now, if the individual chances we said are r, this is really just equal to r cubed, right? We said r is 1/2 in this case, so it's just 1/2 cubed, which is equal to 1/8, right? So the chance of all three tosses coming up heads are 1/8, right? So in this example, we show how we can assign chances to logically complex propositions if we know the chances of the simple propositions together with some assumptions like independence, right? Okay. Now, note that we can also compute the chance of propositions that specify relative frequencies. So, suppose that we let little h be the property of landing heads. Landing heads. Now we can consider a proposition like f d of h equals 2/3, right? This would mean that the relative frequency of heads among our three tosses would be 2/3. In other words, we got exactly two out of those three tosses to be heads. So this would be, this proposition would be true. It would be equivalent to the proposition h1 and h2 and not h3, right? So this would be the proposition that the coin lands heads the first two times and then tails. Or, could be that the coin lands heads the first time and tails the second time, not h2, and lands heads the third time. Or it could be that the coin lands tails the first time, not h1, and then goes on to land heads twice, right? So this big disjunction is really equivalent to saying that the relative frequency of heads in our reference class is 2/3, right? Now, if we wanted to find the chance of this proposition being true, that is the chance that our relative frequency would be equal to 2/3, right? We could do that by finding the chance of this long disjunction holding. But note that each of the disjuncts of this disjunction are mutually exclusive with one another, right? You couldn't both get two heads first and then a tails, and also get a heads first and tails second and a heads last, right? Those would be incompatible with each other. So additivity will apply here. So this is really going to equal the chance of each one of these things individually, right? Chance of h1 and h2 and not h3, plus the chance of h1 and not h2 and h3, plus the chance of not h1 and h2 and h3. Now, each one of these we can figure out in a way similar to the way we solved the problem above, right? So what's the chance that you would get heads the first time and heads the second time and then tails the third time, right? Well, assuming, independence and uniformity of the chances, this would really be just whatever our chance of h1 is, right? Which is just r, so I'll just write that as r, right? R times what our chance of h2 is, which is also r, times whatever our chance of not h3 is. But that's just going to be 1 minus the chance of h3, which is going to be 1 minus r, right? And then we add that to itself again. So we have this plus, I'll just write this as r squared times 1 minus r plus r squared times 1 minus r, right? Because each of these terms, this sum, are going to be the same, right? Because here, all that really matters in computing the chance of one of these sequences is actually the relative frequency of heads within that sequence, right? Or equivalently, the relative frequency of tails within that sequence, right? So they're all going to have the same chance of happening. So then we just get 3 times r squared times 1 minus r. Now, if we assume, right, that the probability, or excuse me, the chance of heads on any toss is 1/2, then we get 3 times 1/2 squared times 1 minus 1/2, which is just 1/2. So we would get, let's see, 1/8 times 3, which would be 3/8, right? 3/8 would be the probability, or the, excuse me, the chance of the relative frequency of heads in our reference class being 2/3. So now we've seen how we can compute the chance of getting a particular relative frequency of a property within a given reference class. Now, intuitively, right, we expect there to be a correspondence or harmony between relative frequency, right, and chance, right? You'd expect the relative frequency of a property within a reference class to be equivalent to the chance that you'd get that property on any individual case, assuming the chances are uniform and independent, right? And it turns out that there is a formal result that vindicates that general intuition. That's an implication of the law of large numbers, which is an idea you may have come across in a statistics class, or may come across in a statistics class. In particular, it's going to be the weak version of the law of large numbers that implies this particular connection between relative frequency and chance. Informally, what the connection is going to be that as, right, D grows, right, as we basically take larger and larger data sets or larger and larger reference class, the chance, that's in the sense of the objective chance, that the relative frequency of any property, let's say x for an arbitrary property, the chance that the relative frequency of x departs from the chance of x grows very small, right? Right. In other words, it becomes very unlikely that our relative frequency of a property is going to depart from the chance of that property if we're dealing with a large enough reference class, right? Right. A little more formally, we could say that, right, for any small amount of error you want to take, epsilon greater than 0, as the size of D grows, right? So, right, remember we used the number function to write the size of D with the universal property as x or not x, right? As this goes to infinity, right, as the size of our data grows, the chance that the difference between the relative frequency of a property x, right, and the chance of a particular entity having that property x within our reference class is less than epsilon goes to 1, right? We could say again informally, relative frequencies approach or converge, to chances. This would be the informal statement. In the long run, right, this is a limiting result. And of course, we had to have some assumptions here, right? We had to assume, right, the uniformity and independence of chances, right? The existence that there even were chances, right? But given that there are chances that have those properties, there is indeed, at least in the limit, this very tight connection between relative frequencies and chances. Okay, in the next video, we'll tie all this together with epistemic probability or rational degree of belief. So look forward to that. And remember to complete the participation poll for this video. And I'll see you guys next time. Thanks a lot.